Good morning, everyone. Good morning. Again, good morning. Yes. Welcome to the Brazilian ICPC Summer School World Final class. Congratulations for you, and I hope you all enjoy these 2 weeks that we are going to be here. We need to give you a brief information of what we are going to have in the next weeks. Where's my presentation? Okay, so I have 5 slides to show you what we are going to have. And the first one, we have the school will start today and go up to February 2nd. We're going to talk a little more about this later on. We have, this year, we have 2 gold sponsors. One is Google, the other one is TFG. Then we have 5 silver sponsors, AB InBev, Samsung, Vitex, Uber, and Venturas Motorola. And we have a bronze sponsor that is Microsoft this year. I would like to thank all of them to sponsor this school and help us to have you here. The school is growing, like the number of participants of all the years. I used the first edition from here at Unicamp. Indeed, we start 3 years before that, but we have a very small school, only for the world finalists, no one else allowed, and only from Brazilian world finalists, and it was held in use. So I tried to collect the data from the years we have here. And this year, we have 177 students registered. And we decided to split into 2 classrooms. So we are going to have the World Final class and the Brazilian Final class. The World Final class, we have lectures in the morning and contests in the afternoon. The Brazilian Final class, they are already in the labs with the contests today, and they are going to have lectures in the afternoon. So you have blue badges, they have green badges, and everyone with red badges are people that are helping you on everything else. So we have instructors, staff, and all people on the support side with red badges. Talking about badges, does everyone have their badge? Who is missing a badge so far? No one, right? Okay. I'd like to play a bet with you. How long is it going to take for someone to miss their badge? What can we do with the first guy who lost the badge? Sorry? What can I do with someone that lost the badge? Sorry?
$10?
$10. We have some problems here, that logistic problems, that we really need you to be with the badge. Like, no badge, no food. Everyone who came here before knows that. No badge, no food. So it's easy for you. You can be hungry, no problem. If you want to be hungry, no badge, no food. So we have a university restaurant and you need to have your badge. So our monitors will identify you and allow you to enter without paying. Okay? So, and for several other things, for lab, for entering in this building, you need to have this badge. And also, if you have some problems with your badge, you need to solve it. Okay? Otherwise, you're not going to get food. This is the main part of the thing. And this year, we have 31 students that are world finalists, this blue thing here. And we have 146 students that are not world finalists. This is the percentage we have this year. And from the summer school, these are the places where students come. Each place of that, each position of that mention at least one student. They may have more students. So people from Mexico, okay, people from Colombia, great. People from Peru, great. People from, there are 2 places in Peru, people from Bolivia, great. People from Chile, people from Argentina, and people from Brazil. Okay. We can have a soccer game this week. Okay, you have a ball, and if you want to have a soccer game, we can organize that. Let's see the results. Okay. So welcome everyone, and it's a pleasure to have you all with us. From the World Finals class, we are going to have in this first week Andrew Stankovic. He's already here. on the second week, we're going to have Adam Barashvili with us. He will arrive next Sunday. We also have Juliana, who is teaching the first week on the Brazilian class. She's attending this opening ceremony here with us. So I would like to thank Andrew and all the instructions on this class. We have a few logistics information here. We are planning to start mornings at 8:30, and Andrew can change this if he wants. If he wants to be earlier or later, it's up to him. We are going to talk to him. And we are going to have lunch from 11:30 to 1:15 p.m. And exactly at 1:15 p.m. the contest will start on the other room. So the labs are exactly in the same buildings on the other side of the building. And afternoon, so we're going to have the contest here, and we're going to have lunch from 6:15 to 7 p.m. We have a very rigid schedule on this 7 p.m. So if you miss this, like you need to have dinner up to 7 p.m. in the university restaurant. So because of this, we need to give you this slot for dinner, then we need to give this slot for a contest because it's fixed size, and then we make back everything. So the main problem is that usually you finish a contest, and what do you want to do? Talk about the problems. So you can talk about the problems walking to the restaurant. Okay, you have a good walk to the restaurant to talk about the problem. If you stay here, you may miss the dinner. Okay, and today we have here Professor Carlos Ferreira, and he wants to talk to you guys at the end of the day at 7:30 today at this auditorium about the logistics from Latin American and Brazilian contests. Mainly Brazilian or Latin America also? Mainly Brazilian. So for Brazilians, can you raise your hands, Brazilians? Okay, come here tonight at 7:30 p.m. Okay? We are going to talk about the Brazilian logistics and everything, contests and sub-contests, everything here. Okay? We are going to define the lunch for Saturday. Saturday will be a different schedule. And we are going to have pizza also Saturday after the contest. Oh, you know the pizza, right?
Yeah.
Okay. And Thursday will be Sponsors Day. We are going to provide you the full schedule. It's already on the web page. It will be on different locations in the convention center. And we have some staff people here. Can you raise your hand? We have Celso and Jonathan. We have those with the red badges here. Oh, there's a few. Sax is also there. And what's your name? Jonas. Okay. So they are there. If you need anything, please ask them. And also, if they ask you to do something, please help go in there. They are going to get you for lunch and go to several different places. You need to create teams. I think all of you already have teams, but if you need to create teams so far. Okay? And I have some thank you slides from our sponsors. I already mentioned that. You have Google, TFG, AB InBev, Samsung, VTech, Uber, Venturas, Motorola, and Microsoft. I'd like to thank again for the sponsors. I'd like to thank again for the instructors, all the instructions, and Unicamp for holding this event, SBC staff, Rafael, Carlos, I also didn't mention your name so far. And based on that, I'm finished. I want to give the word to both Rafael and Carlos because they are saying no. So, Professor Carlos, you need to come here. Yes. That's the good part of having a microphone. You can pass the microphone to someone else and ask them to say something.
Thank you. Nobody lost your budget, but someone lost the cell phone. Oh. It's yours. Oh, no.
It can be mine.
Yeah. Somebody needs a cell phone.
$1.
Yeah, okay. So, welcome. It's a pleasure to welcome you all here in the 8th. It's the 8th school, Brazilian ICPC Summer School. It's a very big success here at Unicamp since 2012, maybe. And it's a real pleasure to welcome Professor Stankiewicz this year, Professor Andrew Stankiewicz from St. Petersburg, ITMO. It's I think everyone here knows him. It's a legend in the ICPC community, and it's very nice to have him here. So again, Rodolfo said we have 24 world finalists. 31 world finalists. Who is going to go to Porto this year? Oh, very nice. Many people there. That's very nice. Who wants to go to the next ICPC finals like next year? No one wants? Oh, okay, someone wants. Okay. Then we have plenty of future world finalists here. Again, it's very nice to have you here, and I hope you enjoy these 2 weeks. It's going to be very much work. I'm very sure of that. Instructors will guarantee that you will work a lot, but you will learn a lot. Yeah, and it's very nice to see that you want to learn and to solve new problems and to learn new things. Okay, Rodolfo said again already. Today I want to talk to some of you, to the Brazilian ones, about the competition in Brazil, to have new ideas and to know what to do to make the whole ICPC competition in Brazil a better experience for you guys. And it would be very nice if you can come 7:30 in this book. Okay? Enjoy, have nice 2 weeks, and welcome to Campinas.
Okay, so let's start with today's activities. Again, I would like to invite Andrew here. Thank you again for being with us, and they are all yours. Do you prefer this one or that one?
Let's try the thing. It works. Here.
Yeah.
Hello, everyone. Anyone? 1, 2, 3. 1, 2, 3. Oh. Okay. Thank you, everyone, for coming here. It is a great pleasure for me to be here on this camp. Just one last bureaucracy thing. It was very difficult for me to get here, and I want to ask you one small thing for me. We have prepared with our university a small agreement for each of you that I teach you free of charge, and you are listening to my lectures. So. That is important for our university ITMO International Cooperation Report. So I would like to ask every one of you to take one of these now and fill it, and then we can go on to algorithms, okay? So I have 3 packs, one for this part of you. They're all the same. Will we distribute it, or will you? Let's try to distribute it, okay. So just one pack, one small thing. You can look at it. I will tell you. It would take 1 minute for each of you to fill it. The left part is in Russian. You don't understand it, so don't put anything there. Although it's the same as the right part. The right part is in English. You can read it if you want. It is some language that I understand, some power paternity and something like that. But the idea is you can read it in the head that it's gratitude education, so it's free. Okay. So, please don't write anything until I tell you what you write. Anybody needs one? Okay. So now, everybody has one. It's the same text actually on the left and on the right. So on the right part, the first page is full name of person, citizenship. Just please write down your full name and your country, and then your university in English. So next pages are just text, and the last thing is again it says student. You write down your full name, country, passport details. Please write down your any passport number or ID number or whatever you have. Anything, they still have no chance to check it, so please write down any of your identification number and permanent address and telephone number. Nobody will call you and nobody will come to your home, I think. So, but please write down, because it's checked by our authorities that it's okay that we don't forfeit this education. So please write down your address and phone and sign, and that's it. So if you wish to read the text, it says that you come and listen to my lectures and you don't make any bad things to ITMO university equipment, but you don't have it here, so you cannot actually do anything bad to it, I hope. And don't do anything bad to Unicamp, this great university equipment also, please. Although this agreement doesn't say this. If you feel it, just raise it and we will collect it. And thank you very much for helping my university to in our nationwide competition for international cooperation. Just write where is the English subscript. Don't write where you see Russian words. Write where you see the English words. You don't know Russian words, you do.
¿Y tú has tratado haciendo así? Tratar de usar zapatillas y ordenar. ¿Cómo se hace como no puedes subir la clase a internet? Claro. O sea, solo que la mitad la sube así.
Please don't put any numbers, dates, or whatever you have, because this thing. If you need on your side something to present to your university that you had a short term in the Russian university, we can make a copy for you also if you need. But I don't know. I think that Unicamp participation is already a good thing, so probably you don't need one. Yes, that's great. That's great.
Thank you very much.
Great. Could you sign? Please sign in the end where it says student. And that's. Thank you very much. Any ID number is okay. Sorry. No problem. Thank you.
What does it mean that we allow for dissemination and altering or adding personal data?
Well, in Russia, we have very complicated laws about personal data. So whenever you assign your name for a university, you must give us the agreement to collect your personal data. It's in Russian thing. So, but I think this is a popular. I'm not sure when it meant dissemination. I mean that probably. It is that's very well. The whole this document sounds very creepy for me, actually. To be honest,
I'll trust you.
our lawyers make this. Okay, I think most of you have completed. If you still have to complete it, maybe we could start with our introduction of today's thing, and you complete it and give it away. So, okay, as you mentioned, my name is Andrew Stankiewicz, and I will be teaching you the first week of this camp. The contest is the contest. It's okay. We will use our university contest system called PCMS. It's located at neufcifmo.ru/p. You will get this in your handouts in the end of the theory classes today, so you don't need to write it down. You will also get a login and password. You will be able to solve the contest from 1:15 to 6:15 every day. And after that, the system will be open and you will be able to try your solutions again if you want to. We call it in Russia upsolving. I don't know how we call it in Brazil, in Latin America. Well, so you will be able to upsolve the problems if you wish. Next day we will have some problems discussion. We will discuss the problems of the previous day, and we will have some theory classes also. Today we have a longer part for theory classes because we don't have previous day problems. So we will probably be talking about some longer topic. Not probably, but we actually are going to discuss string algorithms today. Okay. Where does that work? We will see how many algorithms we will be able to discuss. There are many string algorithms actually. Well, you hear my breathing. It's okay for you, but I hear it. Can we make it, put it somewhere around? Like this. Do you still hear me? Okay. So I will try to see. I've seen. Thank you very much for filling the questionnaire about your knowledge. I will try to tell something new for everyone in each of our theory classes. But of course, there are 90 of you, and it's impossible to find the program that everyone will find everything new and nothing known and will understand everything. So I hope that you will understand most of the things and that every one of you will find something new or some new look at the things you know or something like that. If you don't understand what I say, if you want me to repeat, just don't hesitate. Please always ask me to stop, repeat, explain more and something, okay? Okay, so let's go with the algorithms on strings today. And we will start with two simple algorithms that most of you, I think, know, but we will take an alternative, maybe look at one of them, and then expand it to a more different algorithm. So, what about string algorithms? What is the most basic problem to discuss when talking about string algorithm? That's substring search. Let's make some arrangements. I think it's not focused, first of all.
I have no control over that, sorry.
So, is there any use to make a recording if nobody can then?
I'm trying to zoom in and out as much as I can, but it's a bit hard.
I see. And the second question is, can I have more? Is it enough light? Do you see what I am writing down? Okay. Okay. So that's the substring search. So we have some text. And we have some pattern. And we want to find this pattern in this text. But actually, the substring search problem can have many statements, not only this simple. For example, simplest setup of a substring search is you have a text, you have a pattern, just find all occurrences of this pattern in this text. So it's one text, one pattern setup. For this problem, there are many known solutions. The most common are Z function, Knuth-Morris-Pratt algorithm, or prefix function. Hashes, of course. But the other setup can be, for example, is what if we have one pattern but multiple texts? One pattern, many texts. So what you want to do is you have one pattern and you want to search it in many different texts. In this case, of course, all these algorithms are also applicable, but you can also improve this by processing pattern before you make a search, and then make a search. So we will discuss this setup also today, and it has a solution which is called Knuth-Morris-Pratt automaton. KMP automaton, which allows us to process the pattern, and then build the automaton that allows us to search for this pattern in text in real time. So one character of the text will take 1 unit of time to process. This method can be generalized to a setup with multiple patterns, multiple texts. When we have multiple patterns and multiple texts, and we want to search for all of these patterns in these texts. In this setup, we can generalize KMP automaton to get so-called aho-korosik automaton, which allows us to search for multiple patterns. Well, the question is, when can we have multiple patterns, one text? Of course we can. But if we can solve the more general problem, we don't need to consider this simpler one. In this case, we have pattern before we have text. But what about the opposite situation? We can have a text before a pattern. So for example, let's consider this setup. One text, multiple patterns. So we have a text, and we want to search for multiple patterns in it. In this setup, we can process our text before we consider our patterns. And that actually allows us then search for patterns in a time proportional to the length of the pattern, not the length of the text. Only text preprocessing takes time. So in this case, there is a real big set of structures that can work with this setup. It's called suffix structures. There are 3 well-known suffix structures: suffix array, suffix tree, and suffix automaton. I think today we will talk about suffix array, and maybe in one of the following days we will talk about suffix automaton or a tree, we'll see. So, this can also be generalized further to multiple texts, multiple patterns. The difference between these two setups is that what you preprocess, patterns or texts. So, do you want to preprocess what you are searching for or what you are searching in? That's the difference. So, okay, let us briefly consider these 2 algorithms, because I think that most of you have already known them. If I read your questionnaire, most of you know them. But let's talk the same language, so just use our few minutes to consider this. So let's start with the Z function algorithm. Let's see. Let's take a string S. So that function for that.
Sorry, could you please move the banner?
Yes, let's move this banner. Is it allowed to move this banner away, or must it be in the center with the sponsors?
As much as you can, leave it in the center. But you can move it a bit aside.
Okay. Okay. Is it okay? Does it?
Thank you.
Okay. Thank you to our sponsor, because if there were no sponsors, none of us would be here. So it's very important, actually. Okay, so let's see. Let's take a string S anyway, and consider the following function called Z function, which takes a position in S. Okay, let me ask you a question. All of you, what languages are you using? C++? Everybody, almost. Java? Python? Python for easier problems that you need a fast code? Okay, I recommend actually, because Python can give you a very big advantage in programming contest. If you use Python for the first problem and save 10 minutes and solve 10 problems, that's 10 minutes by 10 problems multiplied in penalty time. So. Okay, so that function, so the question was actually not important because all of the modern languages index arrays from 0. So we will use 0-based notation for our arrays and strings. So that function takes an index of our string and gives us a number, well, from 0 to n minus 1 actually, so that for I is maximal value such that the first I characters of S, the first J characters of S are the same starting from the beginning and starting from the ith position. Like this. So we don't put that for 0 because it's useless, yes? The string starts at the same position, but you could, if you wish, and set it to n or set it to anything you like. How do you calculate that function? The simplest algorithm is just to use if. So we go for I from 1 to n minus 1. I will use this notation, okay? I will not write some syntax garbage of C++ or Java, something like int, semicolon or something like that, okay? You understand that? Okay, so for I from 1 to n, we want to calculate that function. So we start with, I will leave some space, that I equal to 0, and while S with index Z of I is equal to S with index I plus Z of I, we increase Z of I. Like this. So this is a nice algorithm, but very slow. Because for the string of all equal characters, it works in quadratic time. So we can speed it up using the following observation. Consider some position I. We want to find z function for that position. We have already found z functions for all previous positions. From among those, let's keep the one, consider some position, we have that function for it. So that means that some substring starting there is equal to the prefix of our string, yeah? So this equal to the prefix substring is called a z block. And from among all previous z blocks, let's consider the one which has the greatest end, the greatest index of its right end. So let's see. Suppose that it does contain I. So let's have two variables, L and R. And that means that that block is equal to the first R minus L characters of the string. So we have I here, and consider the same position in this occurrence of this substance. It's I minus L. We know the value of that function for I minus L. And it goes to somewhere. So it's another Z block starting there. So this intersection of this Z block and that one is the same here and there. So actually the intersection of our Z block that we keep, this one from L to R, and the one for I minus L, is the same here and here. So we don't need to make these comparisons, and we can improve our algorithm by starting not by 0, but with this intersection. So we remove this and write down something like this. That I is equal to the minimum value from among R minus I and Z of I minus L. You see, this is if this blue one goes out of our Z block, then we know up until here, and if it doesn't, if it stops here, then it's up to here. Okay, and then we do the same thing. It's okay, but we need to keep L and R also. So actually we see if I plus Z with index I is greater than R, then we just say L is I, R is I plus Z of I. So, this way, we have something better, but still we don't know. Does it really work better than previous one? Actually it does. Let's see. This minimum, if it's here, so this blue block is small, then the next character here and here are different. So here we have some A, some A, some B. So this while cycle will not make any iterations. It will stop immediately. If this blue one goes beyond this black one, then let's see, we start comparing at this position, and these positions are different actually. They have different characters, because in the other case we could expand the black one. So again, this while will stop immediately. Why do we need while at all? The problem is that if the blue one had the same length as the black one, then we have this character is different, A, C, B, and this one is not B, not equal to B, but can be equal to A. In this case, this while will increase the value for Z of I, but each time it does, it increases actually the value of R that we will then use. Because it goes here, so here, here, and here, and the new value of R will be greater. So since the value of R never decreases, and each iteration of this while increases it by 1, the total number of iterations is less or equal than n. So that's the algorithm for that function. It has actually 2 minor bugs in what I have written at the whiteboard. The first one is that what if we go out of our string? The actual way to solve it is to add some so-called sentinel character to the end of the string, so which is not equal to any character of our string. For example, 0 code character. It was very useful when we had C strings, like character star, yeah? So which already had this 0 in the end, but in C++, string class doesn't have this, so you need to add it manually. The other question is, what if r is smaller than I? In this case, this would be -1 or -2 or something that would be negative. So actually you need to add something of that I less than 0, then z of I is 0. Something like this. So with these two fixes, I think that that's the correct implementation of that function. It can be a little bit improved with minimals or maximals and something, and here we can always assign r to z of I and something, but I think it's more clear this way. Okay, so this was our first algorithm. I think that most of you have heard about it before, and what I want to ask you now is, because for the known algorithm it's always easier to understand, is a question, give me some feedback. Is my English okay for you? Do you understand me okay? Okay. Is the speed okay for you? If you didn't know this algorithm, would it be okay for you or slower? You can't tell. So let's go like this for a while. But if you feel that you are lacking behind, don't hesitate to raise your hand and ask a question, okay? Okay, any questions on this, on that algorithm? No? No? Okay, how do we use that function for what we have stated here for our problem of one text, one pattern search? It's easy. We do the following. We put the pattern first. Then we make a separator character. I denote it as a sharp character, but if it is in your alphabet, you use some other one, of course. And then you put a text. And you find that function for this whole string. Let's see, if the pattern occurs somewhere in our text, then that means that from here we can read the pattern which is the same as we have prepended in the beginning of the string. So that means that in this position that function is equal to the length of our pattern, say m. So if you find a position where that function is equal to m, then this is the occurrence of our pattern, and vice versa. This algorithm clearly needs m plus n time, but what about memory? This simplest implementation that we have here uses also m plus n memory. Actually, when we make a substring search, in general we usually have shorter patterns and longer texts. So what we would like to do is to save on memory, don't have additional memory proportional to the length of text. Let's see, do we actually need to keep our z function values? The answer is yes, because we reference them here. So we need z I minus l. But what is I minus l? I minus l is the value for that function, the length, the distance from the current position and the start of the last z block. But this distance is not more than the length of the z block. And the length of the z block does not exceed the length of the pattern in this case, because we put this separator character here. So we actually only need to store in a permanently the first m values of our z function. And we don't need to store this part of the array. We can just calculate it and use it to look for pattern occurrence. So this gives m plus n time and m memory. This is not very important for that function actually, but it will be important for the next algorithm that we're going to consider, for KMP algorithm in our transformation of this algorithm to suffix O to KMP automaton. So, okay, if we are done with that function, let's go on and move to the next algorithm. Prefix function algorithm, also known as Knuth-Morris-Pratt algorithm. Okay. Okay. So the prefix function or pi function, prefix function is the following thing. So we have again the string s and the position of this string I, but this time we are not looking for a prefix starting at this position and equal to the prefix of the string, but we are looking for a suffix ending at this position and equal to the prefix of this string. So these two black substrings must be equal and the length must be maximum possible. There is a degenerate one. We take the whole part of the string from 0 to I. It's not okay. We don't want this big string. So our definition is the following: the pi of I is the maximal value of j, such that if we take the first j characters of our string, s from 0 to j minus 1, it is the same as if we take the last j characters, or something like s from I minus j plus 1 to I. And of course we don't want the whole string, so j must not exceed I. Well, with these zero-based characters, zero-based indices, we need to use some consideration when making these plus minus 1 things. So here my less or equal, because actually j is the length of the prefix, and it may be I, because in this case it would end here at I minus 1 position. So the length of this big prefix is I plus 1. Okay, so how do we calculate prefix function? Let's see. So we have again calculated it for previous values, and we want to calculate it for I. Let's consider I minus 1. We have some value for I minus 1. These two substrings are equal. Let's take our next characters, x. Is it the same as the character after the prefix of the length that we consider? If it's the same, then we expand it by 1, and we are done. It cannot be greater, because we could, should it be greater, we would cut away the last character and get a better result for I minus 1. So it's the answer in this case. The worst case is if it's not equal. So this way we are left with a new problem, and we don't, at first glance, we cannot use the result from the previous one, but actually we can. Let's see. So we have another, let's consider the answer. So the answer is some prefix, that ends with x. And it's also here a suffix ending with an x. So if we cut away this x, we get some prefix equal to suffix for this string, which is equal to this one in turn. So what we need to do is to go back to that shorter one, this string, and take its prefix equal to suffix. Check it again. If it's not okay, we curse, and so on. So let's see. Let's make it like this. So again, we have pi of 0 equal to 1, or equal to 0, of course. Equal to 0 because that's the only j that satisfies j less or equal to 0. And for 1, 2, and minus 1, we go and search in the following way. So we have some value, say, call it k, equal to pi from I minus 1. We try to find, we try to check that the next character, so that's 0, k minus 1, k. So it's I. We check that the character is position k is the same as an I. So if it's equal, then okay. If it's not equal, so s with I is not equal to s at k, then we should go to the best possible suffix of this, so the prefix block, yeah, that is equal to its prefix, and it's pi function for k minus 1. So we would move to this one, and this would be k, this would be k minus 1. So we would go to, so here we have a while, and we would go to pi of k minus 1. But the problem is, we can't, what if we never find such position that the next character is equal to our ith character? Then we must stop, and the answer is 0 actually. There is no prefix of our string that is equal to a suffix ending at the ith position. Oh, well, okay. If k is equal to 0, if we're already at no prefix, then okay. Let's stop and take a look. And k is greater than 0. Okay, so we stop and let's take a look. If the next character is okay, then we increase it by 1. If s with I is equal to s at k, we increase the k, and the pi of I is k. So that's it. And the closing bracket from that function will work again. Okay. So what we have here is the prefix function algorithm. It looks strange actually. Should I have known all those explanations, it would be absolutely no idea why does it work so. But I hope that those explanations show you why plus minus 1 indices. It is correct, I think. No, I believe. So this minus 1 is because when we look at the case character, we want to move to the prefix function of the previous, actually. And this minus 1 is a key. So it's like this. This algorithm actually has is also linear of n time, because let's take a look at this while. It says if it stops, okay, it stops. If it goes on, it says k is equal to pi of k minus 1, but pi of k minus 1 is less or equal to k minus 1 because of this definition, and is strictly less than k. So each time this while makes an iteration, k decreases. On the other side, it only increases here, and on the next iteration of this for cycle, it will start with the same value. Actually, this can be replaced with this. So we can do this. Okay? So k increases by 1 at most n times, and decreases each time this while takes an iteration. So the total number of iterations in this while is again at most n. I give the following analogy here. So we have a box of sweets, and here we put one sweet into the box, and here we take at least one sweet from the box. So the total number of times we take 1 cannot exceed the number of sweets, unfortunately. Actually, fortunately for this algorithm, because it allows us. Okay, so this is prefix functional algorithm. It was independently discovered by Knut, invented, not discovered maybe, Knut, Morris, and Pratt. So it's sometimes called KMP, Knut, Morris, Pratt algorithm. So it's prefix function. How can we use a prefix function to make a substring search in one text, one pattern setting? Actually, the same way. We put a pattern here, we put our text here, and we make not that, but pi function. And this time we find pattern occurrences not at the beginning, but at the end. So, however, if pi is equal to m minus 1 here, we have found the pattern. The same argument about memory applies. We only need to reference here. We only need to reference pi function for values at most equal to the value of some other pi function. So if it doesn't exceed m, as in our case, we only need to store the first m values. Okay. Now let's see the following. Let's get back here and consider our two previous algorithms that we have made, the Z function algorithm and prefix function algorithm. We have our pattern. We run process and our pattern. Stop here, and we have prefix function values for the inside the pattern, or Z function values inside the pattern. Then we add our text, run the second part of our algorithm to find the occurrences of the pattern in text. But each time we find, but we only reference these values, so we don't need to store these values, the new values for text. Okay, now let's say we come up with some other text, T prime. So then we don't need to recalculate these values for the pattern, or neither for pi function nor for that function. We can start from the same position and move on with a new text, and again find occurrences of our patterns this time. So actually, from this point of view, both of of these algorithms solve this problem one pattern multiple texts in a time proportional to length of pattern plus the sum of length of texts. Because we don't need to process patterns. It's not a big win here actually, because because the length of pattern is usually shorter than the length of text. No need to consider the so long pattern that is longer than text. We can find it in text easier without any algorithm. There are none. So at first sight, there is no win here yet, but there is actually when we go on to multiple patterns, because if we have when we have multiple patterns, if we manage to process our patterns only once, we would get the algorithm which works in time total length of patterns plus the total length of text. And this time when we search for multiple patterns, there is also no limit that the sum of length of patterns is shorter than the length of text. Maybe there are many small patterns and the big text. So not multiplying this by the number of texts gives us actually the asymptotic benefit. From this point of view, it's not clear which of these two algorithms can generalize to multiple patterns, but it turns out that pi function does. With that function, probably it also does, but not so easily. So we will now, although that function is easier to feel, I think, so it's because it's prefix equal to prefix. But unfortunately, we will need to live with that prefix function is the one that we need to that we will now improve. Okay, let's get back to it. And let's take the following look at this. Let's see. So you have prefix function, and you make these iterations. So let's see. Consider you have prefix function for. So let's look at this string S. It in our algorithm is composed as a concatenation of a prefix, then some separator, and then text. That's our S. So suppose that you have processed your pattern and this character, so you are now here, and you go for text. Now you don't want to store this, so this line is no longer executed, so you don't store values to save memory. And you don't make this, of course, so you have some value of k from the previous. So you go for text, for I from first position of text, first pos of t to the end, so something like this. And we have k equal to 0 in the beginning, and we have pi for pattern path. So here we have this algorithm. What it takes, let's see, S of k is the pattern path, because k doesn't exceed the length of the pattern. So k is somewhere here, so S of k is somewhere here. We can replace it with p of k, because the first characters of S are the same as p, okay? Okay, so we have S of, instead of S of k, we book p of k. So the only reference to, so here also, make p of k. So the only reference to S actually is now to the ith character of S. Let's store it in a separate variable, call it C. So C is S with index I. So we change it to C here. C here. C here. Okay. So what do we have? Let's see. This part does the following. It only depends on the value, on the pattern, because we reference to pi for pattern part only. We reference our string s to pattern part only. And on the initial value of k and on this character c. So this box is some function, let's call it, say, go. That only depends on k and c. And it returns the new value of k. Let's rewrite it in a bit. So, go from the value of k using a character c. How does it work? Well, this is while and if. Let's change it a bit the following way. Let's move from iteration to recursion. So instead of making while and changing k, let's make a recursive call. It would be the following. So if we start, so if c is equal to p of k, we just return k plus 1. In the other case, if k is equal to 0, we return 0. And finally, if this is not the case and this is not the case, then our while would make an iteration, k would get the new value, and we would be at the beginning of our box again. So what we do in the other case, we return go from pi of k minus 1 by, and c doesn't change, so the same value of c. Okay, so this is go function. It's the same. It does the same as the code in the box. Everybody agrees? Okay. I just changed while to recursion. The question, why did I do this, is the next question we're gonna consider. Now let's remove this box. We don't need it anymore. And put k is equal to go from k by c instead of it. Now the trick is, this go function doesn't have too many possible arguments actually. It only has a k from 0 to m and c from our alphabet. Actually, no, well, it depends on our alphabet. It can be some English characters, so zeros and ones, or whatever. So c is from our alphabet. So what we can do is actually we can calculate the values for this go function for all possible arguments and store them in the array instead of making this function calls. So it would be go key c. Should we do this? And this string would be, this line of code would be k equal to go k c. And the magic is that now it takes a constant time to process the character, not well, what we had before, we had the linear time, but for a particular character there could be many steps because this while function could go and go. Of course, each time it does, it loses its potential, decreasing the value of k, and it will not do it the next time. But this time, our change made our algorithm so-called real-time. Now, any character of our text takes constant time to process. So we remove the amortization from our time asymptotic. How do we calculate this as an array? Well, okay, this function is clearly defined as recursive. This value is smaller, so we just go over larger and larger values of k, and for all c we find this. Now I would like to ask to remove the square because I want this backwards. Can I ask somebody please? Okay, thank you. There is a good way, that's why we need the new board. There's a good way to visualize what we have done here, which is called the DFA, or deterministic finite automaton. So let's see. Consider again our text. We have a pattern and then we have text. So we pre-calculate everything for pattern. Actually, the same idea can be used to remove amortization from calculation of pi for pattern as well, but it's not so important for us yet. And we find this go function, and then we go to this text. So we start here with k equal to 0. Then we take our first character of our text, and we have the new value of k, k1, say, so k0. Then we have the second character of our text, and we have the new value of k, k2, and so on. So we can look at this as the process of taking character after character and keeping a state of this process, the current value of k. So we have the automaton, finite automaton, with states, possible values of k, state 0, state 1, state 2, and so on, and state m in the maximum. And our function goal is actually the transition function of this automaton. It says, if, let's consider some example. For example, let's take a string AB, ABB. Or maybe, no, that's the other way around. AB, BAB. So let's see. When we are at state 0, we would have 6 states. 0 to 5. What does the function go say? It says, if you are at some state k, and the next character of your pattern is the same as the character you want to make a transition, go to next state. So that make this series of transitions. What the other thing says? It says, if you are at the starting position and the character doesn't match, stay. So for B, hello. For B, you stay there. Maybe the batteries are running low. I don't know. This was okay. And the other thing says, if you are at some state and you don't know where to go, okay, go to the prefix function and then try again. Okay, so we need to get prefix function to this automaton. To get things worse, the prefix function for this automaton is called the suffix link. It's not very convenient, but that's the fact. So we cannot change the notation, so we must get used to it. So, okay, let's define the suffix link for the state k, suff of k, be equal to p of k minus 1. That's the thing where we go if we don't find the transition yet. So, in this case, we would go from the starting vertex doesn't need a suffix link. For this, we would go. So, let's say pi function for this is 0, 0, 1, 2. So, for this, and this we go to 0. For this we go to 1. And for this we go to 2. That's suffix function. And the suffix function allows us to make transitions. How does it? We use this recursion algorithm. So, for example, for this vertex, for state 1, we don't know where to go by A. Okay, we follow the suffix function, then A. So it's A. Here we don't know where to go by A again. So we follow the suffix function and A. Here we don't know where to go by B. So we follow the suffix function and B. Here we don't know where to go by A again, and we go suffix function and A, stay there. A. And for here, neither A nor B are yet defined, so we go by A suffix function and A leads us there, and B suffix function and B leads us here. So what this automaton does, actually, it's no special magic, it just shows, visualizes what would happen in our Knut-Morris-Pratt algorithm if we had k, some value of k on the previous step, and the next character of text would be the value of. Okay, now the final thing that I would like to say before a small break is what about suffix function, pi function, can we all introduce it to our new notation? The answer is yes. Let's see. Suffix function of k is pi of k minus 1. Where did pi of k minus 1 come? Let's go back to our code. How would pi of k minus 1 be calculated? I was equal to k minus 1. So we would start here and go here. So C would be equal to S with index minus 1, which is equal to pattern of k minus 1. And so it's equal to go from k minus 1 by the character P k minus 1. So if we build this automaton from left to right in increasing indices of our states, we can do the following. We create zeroth vertex is basic one. It only has no suffix link, and it has forward edge for the first character of our string pattern, and all others go inside of it. And the following vertex, we take a vertex. If we take a vertex, I think that's the end of the communication zone of my microphone. Sorry. If we take the next vertex, we first calculated suffix link using pi for k minus 1 and go for k minus 1. using Go for k minus 1. And then we can calculate Go for k using our pattern again and the suffix thing, so we can replace it with suffix lim of k. So that's what we do. What we have here is a KMP automaton. It has one benefit compared to just plain KMP like this. It is real time, so it takes exactly constant time to process. And it has some bad things also, because it uses, automaton uses m times c memory, where c is the number of characters, because we need to store this Go array. We will now make a short break of 5 to 10 minutes, and then continue to generalize it to multiple patterns, and we will also have this trade-off: real time or more memory, or no real time, amortized time, and some more complicated code, but save on memory. So please take your time to have a short break, and if you still didn't give me the agreement, please do it if you don't mind. So please, let's go back. Let's go back and continue. Continue. Yeah, thanks.
Sì. Oh sì, vamos tanto. Sì, sì, bueno, sì. Giovane meraviglioso. È una cosa. Pasó casi como una área. Igual te quedó mucha dormida.
Para mí, distintivamente la real es lo más difícil.
Okay, so let's try to go on. What we have again, we have evolved a bit our Knut-Moritz-Spratt algorithm, our prefix function algorithm, to what is called pattern matching automaton or Knut-Moritz-Spratt automaton. It's shown for some particular pattern on this whiteboard, and it has the following structure. It has states for all characters, for all positions in our pattern, and its transitions are organized in the following way. When you find the next character of your pattern, you go to the next state, and if no, you have special additional arrows, transition suffix links that represent actually the prefix function. The prefix function, so suffix link for the state k is the prefix function for k minus 1. And if we don't have a transition, we would go to along the suffix link and then along the transition. The thing is that when you store it like this, you use a lot of memory. You use alphabet times more memory than just storing prefix function. The benefit is that you make free moves, not free, but constant tempos. The other way is not to store all the transitions, but only to store suffix links. In this case, you just can calculate them as the ordinary prefix function, and then you can make transitions by recursive call. So you don't store it in the array, you just make move along suffix link, and then along the transitions, the basic one, the one that only move forward. This would be equivalent to default Knut-Moritz-Spratt search algorithm, and the same amortized argument works. We decrease the number of the state every time we follow the suffix link and increase at most by 1. So the total number of decreases doesn't exceed the number of characters that you have seen. Okay. Now what we're going to do with that is we are going to generalize it to multiple patterns. To do this, we need the new structure, the new data structure for strings that is called a trie. try is a data structure. The name was invented by Donald Knuth. The argument for this name is that it is quite looks like the word tree, a bit different, and it's also a substring of the word retrieval. So it's something like that. So it's called, and Knuth thought that it would be pronounced tree, but it isn't very inconvenient because tree is a tree, so people got used to pronounce it as try. It's not also very convenient because try is also a word in a modern computer language, but okay. In string algorithms, try is a try. So okay, what is a try? We consider that we have several strings and we want to store them efficiently. What we can do is to store them in a tree-like structure by, say, compressing their common prefixes. So, say you have words A, B, A, B, A, B, B, A, say something like A, B, and B, A, and B, A, B, for example. Then you could do the following. So say you have A, B, A, B, and then we draw a tree. Here we have the root, so we follow this A, B, A, B. So here the word A, B, A, B, and then we would like to store A, B, B, A. We will say that A, B we also have here, so here we want to go B, A. And A, B again, we have already A, and we only add A, B. So this tree, that the one that we see here, is a trie. So we have vertices that correspond to prefixes of all our words. And if there is a common prefix for several words, it only has one vertex. And the edges correspond to characters of our words. So when we move from the root to some vertex, we trace the prefix of some word, and to mark the words that are there on our list, we use some marks. For example, we can index our words, and we say that this is the end of the word 1, this is the end of the word 2, this is the end of the word 3. So this way, these two words that we have, BA and BAB, we don't get confused, so we know that BA, the word number 4 ends here, and BAB, the word number 5 ends here. So it's no problem that one word is the prefix of it. If we don't need to differentiate between the words, we can only use Boolean marks. So this is the end of the word, this is not the end of the word. Okay, so if you look at this picture and you look at the rightmost picture on the board, you see some common things. So we have again vertices, some nodes connected by edges, and there is a letter on each edge. And for each vertex, all outgoing edges have different letters. So in some sense, there is something in common. And a trie can also be considered as an automaton, but not very interesting automaton, because it only this way we only can consider words that are in our list or their prefixes. And the automaton on the right is actually a bit more powerful in some sense, because it's the opposite. So let's see. This vertex, the last one, corresponds to finding a pattern in our text. So we call it a terminal vertex, say. And when we take some text and go along this through our automaton, each time we come here, we have found the pattern. This is not the case for the trie yet. If we take some text and try to go along our trie, either we found the word that is the prefix of the text and also the pattern, or we don't know where to go and we stop. So what we're going to do now we're gonna combine the idea of prefix function and the idea of a try. We're going to modify this try to add the transitions, missing transitions. So for example, you see here you don't know where to go if you find A again. So that we could search for multiple patterns. There are actually several tricks that we will need to use. So let's go along them and see how it changes. So what we're gonna do, again, we have some multiple patterns. I would like to use some other set of patterns. Let's see. Let's make some smaller set of patterns. In the other case, we will not try to do it. So say A, B, A, B. I would like to have A, B, B, A, and A. So let's take some smaller set of patterns. In the other case, the automaton would be very huge. So again, let's draw a try. So A, here we have pattern number 4. Then A, B. Let's say A, okay. A, B, we have pattern number 2. A, B, A. No, I think we need, okay. A, B, A, B is number 1. And B, A, we'll have B, A. Pattern number 3. I think it's enough. Okay. So, what we're gonna do? How is pattern matching works for the automaton? We take text one after one, and the state is actually the prefix function value. And what is the prefix function value? It's the longest prefix of the pattern. That is the suffix of our text that we have read so far. Let's try to generalize. So we have text, we are reading it again character by character. We want to have some state. What is the state? It's the longest prefix, but of which pattern? We have multiple patterns. Let's say the longest prefix of some pattern, that is the suffix of our text. Let it be the state of our search. In this case, since the vertices of the try are exactly the prefixes of our patterns, the state of our search would be the vertex of the try of our patterns. Okay? Okay. Then, what we need to do is to answer two questions. How do we make transitions? And the second question, how do we find patterns? Why the second question is important? When you are here, for example, you're not the longest prefix of some pattern that we are at is ABA, but we also have BA and A at that position, which are our patterns. So the vertex, it gives us enough information, but we need to find this information. So it's not only the simply when we pass through the vertex with some number, then we have found. It's not that simple, unfortunately. Okay, but let's start with the transition. So again, if we have some state, so for example here, so we have something like A, B, and we find the next character is the one that is in our try, like A here. So it's easy, we just move on. So the longest prefix of some pattern that is the suffix of our text increases by 1, it cannot increase by more than 1 anyway. The other case is that we don't have this character. Then what we need to do is something similar to what we did in Knut-Morris-Pratt algorithm. We need to find, so here we are, here we have some prefix of the pattern. The next character is not okay, we don't know how to move. Then we need to cut our prefix to some other prefix of the pattern that is the suffix of our text and try to go and so on. So what we need to do is to find the next prefix. That is the suffix link for the trie. So consider u to be the vertex of the trie. Then suffix link of u is the vertex v, such that let's say that S of u is the string that we read when we go from root to u. So, for example, for this vertex S, well, this is u, then S of u is AB. Yeah? So we want to find such vertex v that first S of v is the suffix of S of u. So we have some arrow suffix. And from among those, we need u, of course, v is not equal to u. And from among those, we need the one which corresponds to the longest suffix. So, len of S of v is max. That's suffix links for trie. Well, let's try to find them by hand. So, for the root there are no suffix. There is no suffix link because, as in case of prefix function, we cannot find any other vertex that corresponds to a suffix. So, the children of the root, the vertices that corresponds to length 1 strings, the only length 0 string is an empty string, so their suffix link go to the root. Now, next. So here we have A, B. B. B is in our trie, so we go to B. As you can see, unlike simple one string automaton, here suffix link can move to some other subtrees completely. So there is no easy generalization so that you consider each path separately. You must move among different subtrees. So for this vertex, for example, BA, again, A is the suffix link. So BA, BA exists in a trie, so we go to there. And for ABAB, BAB is not there. We don't have BAB in our trie, so we don't go there. And AB is there, so we go. So that's suffix links. We will soon learn how to calculate them, not by looking at the trie, but for some, again, formula. But for now, we have them. So, the transitions. How are the transitions added? So, if we can go down, we go down. If we cannot go down, what can we do? We must go along the suffix line again and try to go along the transition from that vertex. If we find these transitions one by one going down in such breadth first search, then transitions for those vertices that we have already investigated would be known. So we can do the following. We convert our trie to automaton using the following formula. So we have go from the vertex u by a character c. So what do we have? We go along a trie h, so we call it trie uc, if it exists. So we always go down if possible, yeah? It's because what we want to store in our state is the longest prefix that is assigned. If it doesn't exist, if we are in the root, then we stay in the root. If we are in the root, we stay in the root. And if we are neither in the root nor we can go along the trie, we follow the suffix link and then go from there. So we go suffix link of u by the same character c. Okay. Now let's see the suffix link. So that's the definition, but how do we calculate that? Okay, let's see. We have it is very clearly seen here. So for AB, we have calculated it was B. So for ABA, what is the idea? For ABA, it was BA. So we moved along A here. We similarly moved along A here. So it can easily be seen that it is true in general. Similarly, it should not more express. So if we can move along this character from that vertex, we do it. If we cannot, okay, we need to go along a suffix link from there. But going along suffix links is already encapsulated in Go. So we can write the following from a suff from U is root if parent of U is a root. Otherwise, we go along the suffix link of parent and then along the character that leads to us. So we go from suffix link of parent of U. By what character? So here, let's look here. So we are at ABA. We go for a suffix link of BA and go along A then. What is A? It's the character that leads to our vertex. Let's call it enter for U. So enter of U. Enter on edge to U. So we would go from suffix link of parent of U by the character that enters into U. Or if you look here, it is exactly what is here for one pattern. The difference is that here we could easily reference to it as the character with some number of the pattern, but in case of a try, there are many different transitions, and we cannot generally write what pattern we are referring to. So we store for each vertex what is the character that enters it, so we go on. So this is mutual recursion again. If we come to some vertex, we first calculate suffix link for it. It only needs suffix link for its parent, which is higher in the tree, so it has smaller depth. And then we can calculate Go for this vertex using this recursion. We will talk a little bit later about time memory trade-off here. So it's clear that if we store it in arrays, if we use two-dimensional array for Go and store explicitly suffix links and Go, we need the total number of vertices doesn't exceed the total length of patterns, so the sum of length of patterns times the number of characters. That's because we need to store Go for each character. We can, again, not store a Go, but store only suffix links and calculate Go each time, if we need it. That's okay, because when we go along a suffix link, we decrease our depth. So if we go along a simple edge, we increase our depth by 1. So again, the total number of moves when we go along suffix links doesn't exceed the total number of descents. So the total time would be linear in the length of text, and we store and we save on memory. Well, okay, let's try to use it. So let's remove some we don't need. Okay, so let's try. So for the root, we have both transitions. For this vertex, we have a transition for B down in our track, and the transition for A is missing. We must calculate it using this formula. So we go from along the suffix and end by A. So actually we stay in this vertex using A. The same for this vertex, for B, we go by suffix link and then by B, so we stay in this vertex. Then, for this vertex, we have A transition and B transition, suffix link and B. So you see that it gets clumsy because it goes to different subtrees. Okay. Now, okay, for this vertex, we don't have neither A nor B. For A, we go along the transition and by A here. And for B, we go along suffix link and B. So B leads here. Let's see. So if I have BAB, we don't have BAB as the prefix of our pattern, but we do have AB as prefix. So we go here as for AB. And so on. So here we don't have B transition, prefix link and B. Oh, B, we already have it. So here we don't have A, suffix link and A. We go there. That's actually because we don't have two A's anywhere in our pattern, so we need to drop down all but the last A. And for this vertex, we have neither A nor B, so for A along the suffix link and A here, and for B, suffix link and B there. So what we have here is the automaton that we get from our trie. We could use, again, both of these formula to build it in linear time. We could go from up to down, and when we come to vertex, first we go along suffix link of the parent and the same character to get the suffix link, and then when we have a suffix link, we can build transitions. And we can, in general, not store transitions, but save memory and use recursion. But anyway, if you store the trie, the simplest way to store the trie is the same two-dimensional array. And if you already store the trie like this, then you don't lose on memory anything, because you only fill the cells in the trie's data structure that were not used at all anyway, but they were reserved. Okay, so now let's try and search for our patterns in some text using this automaton to see our problems in this process. So let's take a word AB, AB, AB. Okay, so we start from the top and we see A. We come here, this vertex has 4, so that means that we have found pattern number 4, that's A, that's great. Now we go on and we see B, we come here, and that means that we have found the pattern number 2, that's AB, perfect. Now A, and we come here. This vertex has nothing, so we at first glance don't find anything here, but actually we should, because there are A and BA both in this position. We are here. How can we find them? Well, actually the answer is simple. What are the patterns that are mentioned at some point? These are all the suffixes, all the patterns that are current suffixes of the text. What is our state? Our state is the longest prefix of some pattern that is the suffix of this text. How do I find all states that are suffixes of the text at this position? We follow the suffix links, and all the vertices that we meet are exactly the vertices that are suffixes of the text at this position. So if we are here, we must go here, here, and here. So it's A, B, A. Also B, A, and empty string are all suffixes of the text at this position. So we follow these links, and we find patterns number 3, BA, and number 4, A. Question? Okay, then B again, and we are here, so it's 1. We have found the pattern number 1, the longest one, AB, AB. Also, we follow the suffix link and see that we have found pattern number 2. Nothing here, nothing here. So, we have found also pattern number 2, which is AB. So on we go, and by A we come here, and this is a well-known vertex for us. Patterns number 3, BA, and number 4A. And finally we all again descend here and find 1 and 2 again. A, B, A, B, and A, B. Okay, so building automation takes the number of vertices on a try maximum the total length of operations times C times the number of characters, and searching takes, well, okay, walking along the try, no matter do we go as a two-dimensional array or we use recursion anytime, it takes asymptotically the length of text. But the surprising thing is that printing the answer is the most time-heavy thing here, because if you see the text here has length 6, and the number of occurrences of patterns is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have around 10 occurrences of our patterns in a text of length 6. And it's easy to create an example with the quadratic number of pattern occurrences. We just take the text of all A letters and the patterns, pattern 1, 1 A character, pattern 2, 2 A characters, and so on. So this way we have the total number of vertices in a trilinear actually, but the total number of occurrences of patterns quadratic for each position. All patterns that we have not short enough, yeah, match. So what can we do with that? The first thing we can do, if we don't need to find all occurrences of all patterns, for example, but the first occurrence of some pattern, we can, whenever we hit the vertex that has some pattern, we stop. So, but it's not okay, because should we have only pattern number 1 and 3, then here we would still need to go along suffix. So, okay, so we need to. The other thing we can, for example, calculate the number of total occurrences. We can, for each vertex, find the number of patterns on the path from this vertex to the root, and just sum up this number. So that depends on the problem. What we're gonna do now, we're gonna make the final step on this algorithm. We're gonna find all occurrences of all patterns in the time to build the automation, plus the length of the text, plus the answer. What we do now, by simply walking and then walking along suffix link to the root, doesn't still give us this asymptotic, because we make useless moves. Let's see. When we were, for example, here, we have pattern number 1, pattern number 2, nothing here and nothing here. So these last two moves were useless. If we take this example, let's take the example. Let's take two patterns. One pattern will be A, and the other pattern will be A, and so on, and A 100 times. The automaton for them would look like this. A, and so on, A, the suffix links for all these vertices would go to its parent. But only two vertices will have the end of the pattern. This one 1, this one 2. If we run the text of all A's through this automaton, each time we are at some vertex, we will go up to the very beginning, to the root of our tree, and without doing anything good. So what we're gonna do, we're gonna introduce the next notion is the super suffix link. The super suffix link will go from a vertex to the closest vertex along the suffix link that has some pattern in it, or to null, if there is no such vertex. So, for example, this vertex, the root has no suffix link. This vertex number 4 has no good suffix. Vertex is reachable via suffix links. So the root it has nothing, so it will go out. This vertex also has nothing interesting, it will go out. This vertex has nothing interesting, it will also go out. This one has 4 reachable, so it will go here. This one has 3 reachable, so it will go here. And this one has 2 reachable, so it will go here. Not very interesting for this example, but you see, the only interesting step was here, because should we go to the root, we will go here and there, and that would be 2 steps, and here we immediately go out. For this example, this one would go out, all these ones would go here, because the closest vertex reachable by suffixing that has some pattern in it is this one, and this one will also go. So instead, if we use super suffix links instead of plain suffix links when searching for patterns, we would make the number of steps equal to the number of occurrences. So that would lead us to this answer result. So how can we calculate super suffix links? Let's move this nice posture a little bit here. Okay, how do we find super suffix links? It is equal to nothing. Well, it is equal to suffix link of u if suffix link of u is pattern, or to what? Or to null if suffix link of u is a root. And in the other case, it's not the pattern, it's not the root. Where should we go? We should go to the same place where we go from our suffix link. So it's super of suffix link of u otherwise. So this is super suffix link, which is quite easy to evaluate, and they allow us to do better things on pattern matching with this automaton. In particular, if we want to find all occurrences of all patterns, we can do it by following super suffix link from each vertex, in which case we get this complexity for searching length of text plus the answer. They can also improve on some other problem statements. For example, if we need to find the first occurrence of each pattern, then what we could do? We could do the following. If we move along the super suffix link and find something, for example 3. So this has been found. So we remove the marker from this vertex. Now this vertex is void, it's bad. But okay, we can do the thing similar to path compression in disjoint set union. When we go to along the suprasuffix link and it's not needed anymore, we replace the suprasuffix link to the parent vertex. So this way, we gradually remove all useless suprasuffix links and find, for example, the first occurrence of each pattern. Well, this automaton can also solve some auxiliary problems, not only string searching, as well as for one pattern, as well for multiple patterns. For example, we can solve some counting problems. Consider the following problems. The number of texts that contain our pattern. How can we solve this problem? Okay, let's move here. If we have one pattern, for example, we can do the following. First, when we have found the pattern, it's already okay for us. We don't need to search anymore. So, we modify this automaton a little bit by replacing these links to stay in the terminal vertex. So we don't need to search for anything now anymore. Yeah, we need to only find we have found, okay, verified. So now we can find the number of texts of length L that contain a pattern. We use dynamic programming on this automaton. So the idea is we count the number of strings of length I. Let's swap the names of length I that lead to vertex U. So the transition is easy, so it's easier to make a forward dynamics. So we say, so we have count here, so we add character, we consider characters one by one and increase by one, by all characters, so CNT I plus 1 V for other vertices. So, for example, we have one string of length 0 from the vertex 0, at the vertex 0, so the same. So we have vertex 0, 1, 2, 3, 4, 5, 6, no 6, 4, 5, and length 0. So for 0, we have only one string of length 0 that leads to vertex 0 and no other. Okay, so when we go to length 1, we have from 0 a transition to 1 and a transition to 0. So we have one vertex that leads to vertex 0 and one that leads to vertex 1. Okay, I was missing the sound. And zeros anywhere. Now to the vertex 2. From 0 we move to 0 and 1. From 1 we move to 1 and 2. So we have like this, and so on. So that's dynamic programming that allows us to count this number. And the answer is in the vertex 5 for the length L. If some of you know how to speed up dynamic programming like this using matrix multiplication, then you can easily count this number for larger L's. If you don't know, we will probably consider it some of our future topics. Okay, so similarly we can work with multiple patterns automaton. So we can probably do something with it and then analyze it as a graph. Find the number of paths in it, find the number of strings that move this way or that along it, and so on. So not only pattern searching, but solving some other problems on this also. I will give you a last example of the problem, and let's move on. The problem is you have a set of patterns, and you want to find the infinite string that has no pattern as a substring. So consider our set of patterns. Do we have such infinite string? The answer is yes. If we take a string of all B's, all of our patterns contain at least one A, so we will avoid all of our patterns. How does it correspond to our automaton? We start here, go here, and cycle here, and don't visit vertices that are terminal, or visit vertices that have possible terminal vertices that can be reached by suffix links. So in general, how do we solve this problem? We mark all vertices that are terminal. Then we mark all vertices that can reach some terminal vertex by suffix links. And if what we are left with is the acyclic graph, then there is no way to move indefinitely without visiting a vertex that contains a pattern. So there is no infinite string that avoids all these patterns. And if we have a cycle that is reachable from the root, like in this case, then we can find such infinite pattern, infinite string. It would actually always have a structure of prefix and then a repeated suffix. There is an infinite string that avoids all the given patterns. Well, okay, let's summarize what we have talked about in this pattern matching, and we are really quite sure. Okay, so what we can do? We can generalize prefix function algorithm in the following way. First, we transform it to automaton algorithm by building this automaton that corresponds to the states of this algorithm. What is the longest prefix of the pattern? That is the suffix of our text. And the transitions describe how this information changes based on the characters of our text. Next, we generalize it to multiple patterns by first building a trie out of our patterns, and then we can walk along this trie again by keeping the state of our search at the longest prefix of some pattern. We have multiple now of some pattern that has occurs as a suffix of our text, and you can improve this trie, make this trie and convert it to the automaton using this formula, and then work with that to look for patterns or to analyze the set of patterns. The main feature of these automatons is not only that it can search for patterns, but it can also analyze this set of patterns as a whole one, the whole thing. This automaton, it contains all these patterns in some sense, and their interferences, the prefixes that are suffixes of other patterns, this information is encoded there. So when you try to solve the problem about counting, about analyzing some text, that you must consider the structure of the pattern or the structure of multiple patterns, then this automaton can help you. So you might try to use it when there is some. Like this. Okay. This is all I wanted to talk to you about today, about the problem setting pattern first, text then. So if you have any questions or comments, please do ask or say something. And then we move on. We will start and probably finish all tomorrow. We will start the next part of string algorithms about text first setting, in which well, a suffix function for this. Yeah, you go here. You go p of k minus 1, which is suffix of k, you see? It's a notation. It's more convenient like this, because you see, in the vertex k, say 3, we have patterns 0, 1, 2. So, to the vertex number 3, vertex number is the length, and k in prefix function is the position. Here, go. You mean here you want to write suffix of k minus 1. Yes, that's correct. I'm sorry. Yes, you're right. If anybody did write this down, yes, please correct this. If you compare it to here, yes, you can clearly see that you must write suffix of k minus 1, not directly k minus 1, of course. Yes. Thank you very much. Anybody else wants to say something? Okay, then. What we're gonna do now, we're gonna move to another setting of this problem of pattern insertion, where you're given a text first, not the pattern, and the patterns come after that. So you pre-process not the patterns, but the text, and that actually gives you a greater power, because patterns are usually shorter than text, and if we have something in time proportional to the length of the pattern, that is always good. But in the other case, the algorithms became more complicated, because they must process the text in which we are searching, not the one that we are searching for. Okay, so the main idea that is behind all these structures and algorithms is that you have to when you are looking for a substring is the prefix of a suffix. Let's write it down. It sounds easy, but it's very fundamental. So a substring is a prefix of suffix. So what we need to consider all substrings of some text, we only need to consider its suffixes. And after that, if you can look at its prefixes, then it's okay. So, suffix structures are structures that contain all suffixes of some string in some compressed form that allows to work with them in a nice way. So what we're gonna consider today is suffix array. I think since we only have some 23 minutes until our lunch, and we cannot wait much longer because the contest must go, because in the other case we will not have dinner. So I think that we will go like this. We will now give definitions and see some usage, and tomorrow we will consider algorithms for building suffix array. So, okay, what is a suffix array? Suppose you have a string S, take all of its suffixes and sort them lexicographically. How can we represent that? Suppose you can actually refer to a suffix of S with the index of its first character. So if it has an N, then let's take a string, say A, B, A, C, A, B, A. So we take its suffixes. That is 0, 1, 2, 3, 4, 5, 6, and actually we have an empty suffix which imaginarily starts at the position 7. There is no position 7, so it starts there and immediately ends, so it's empty. If we sort them lexicographically, so the smallest one is this imaginary suffix, empty suffix 7. Then we have the one 6, simply A. Then I think it would be ABA, the one that starts at the position 4. Then the whole string starting at the position 0, so this is empty. This one starts with A. Then the last one that starts with A is AC one, so C. So it's position number 2. Then we go suffix. Then the suffixes that start with B go, so it's 5 and 1. 5 and 1. They start with B, and the one that starts with a C, in this case, is the last one. So this array that gives the order of suffixes as they go lexicographically is called the suffix array of the string S. What is so good in suffix array? The one thing that is quite nice about it is that you can, for example, search for patterns in the suffix array, in the text suffix array, and this great statement. We will first give a simple algorithm that will search in time, let's call M len of pattern, N len of text. So search in time M times logarithm N will be our first algorithm of searching using suffix array. And then we will improve it. So, okay, what we're gonna do? We're gonna make a binary search of our pattern in the suffix array. How can we do this? We take our suffix array and we search for the first suffix of text that is greater or equal to our pattern lexicographically. Let's see. We have suffixes of our text in our suffix array. They are arranged lexicographically, something like this. So suppose our pattern occurs at some positions. Then it is a prefix of that suffix, so it's pattern. So it occurs there, and then suppose it doesn't occur. So it has prefix greater than pattern, and so on. And before it, we have prefixes that are smaller than a pattern lexicography. So if we find the first suffix that is greater or equal to P, that would be exactly the one that starts with P if there is one. Of course, there can be no such suffix. If we find also the last suffix, not the first suffix again, of T that is strictly greater than P, that would be the one after the last occurrence. So between these two indices, F and L, including F and not including L, we have all occurrences of our pattern to our text. So say we have AB and we want to search for it. So we try binary search. So we try in the middle. This one, 0, AB, greater or equal. Okay. Move R here. So from here to here. Then we try the middle. 6 is A. A is less. So we move L here. We try the middle. 4 is ABA. It's greater or equal. We move over here. So we have found F, the first occurrence. Now we want to find the last occurrence. Okay, so we're searching for a great. Again, LR, the middle 2 is ACB, greater. Okay, R here. The middle 4 is greater or is equal. Not good. We want to find not the first suffix of T that is greater than P, but the first suffix of T that is greater than P at first M character, yeah? So, because in the other case, this one is also, strictly speaking, greater than P, yeah? So like this, if we do like that, then at 4 we say AB is equal. So we move L here, 0 again, AB is equal. So we found the first and last here. So we have two occurrences starting from position 4 and starting from position 0. The time complexity is you have to make a binary search which is logarithm n time, and you must compare two words up to the length of the pattern, and that is m time. So it's m times logarithm n. At first it seemed that the plane search is m plus n, and here we have m logarithm n, so m has a multiplier, but usually, of course, if we have a very long text and a quite short pattern, this is still better. And what we will do, we will improve this from m times logarithm n to m plus logarithm n, which would make it strictly better than simple search. Of course, we should not forget that it's not that easy to get suffix arrays, so we need to build it first. So here we have two things to do. Okay, to improve this search algorithm and also to open the door to many other algorithms on suffix array, we will need an additional information about suffixes in our suffix array that is called the LCP algorithm or LCP array. LCP stands for longest common prefix. But let's get back to our example. So what we have here is the suffix array for this string. We will now consider the following. We'll take the suffix from the 7th position and the suffix from the 6th position. That's empty suffix and A. Their longest common prefix is empty. So LCP array, well, it's like shifted 1/2 of the position to the right, yeah, so it's between two neighboring positions. But we can't index arrays with dot halves and so on. So we say that it's for this position, the longest common prefix with the next suffix in the suffix array has 0 length. So now 6 and 4. 6 is A and 4 is ABA. So their common prefix is A, which has length 1. So we have LCP for this position equal to 1. Next is 4 and 0. 4 is ABA and 0 is ABAC, ABA. So the longest common prefix is ABA, which is 3. Next is 0 and 2. 0 is the whole string and 2 is ACABA. Their longest common prefix is the letter A, which is 1. So 2 and 5 start with different characters, so it's 0. 5 and 1 start with BA, both. It's 2. And finally 1 and 3 start with B and C correspondingly, so it's 0. So that array LCP is the longest common prefix of a suffix in the suffix array and the next one in the suffix array order. Okay, let's see how can we use it. For example, let's use let's see not how we use it, let's see how we build it. The first idea is just to build it directly. You just go and you have two suffixes, you just go and calculate their longest common prefix. It turns out that if you do it like this, you will get quadratic time, for example, on the string of all equal characters. Because the sum of all, it works in a time proportional to the sum of these values, and the sum of these values can be quadratic. However, if we change the order in which we calculate the values, it turns out that it can be made in linear time with a very simple algorithm. Let's not find values in order for the first suffix in suffix array, second, third, and so on. But let's find this value first for the position where we have 0. Then for the position where we have 1. For the position where we have 2, 3, 4, 5, 6, and so on. What is beneficial about this? Let's see. Suppose you have your suffix array and you have a position where you have I. So that's the suffix that starts with the position I and goes to n-1 there. You find the longest common prefix with the next string, and it's either 0 or no. Okay, if it's 0, it's very fast to find. The first characters are different, so the cases when the answer is 0 they totally take linear time. It's very fast, okay? If you, again, find longest common prefixes in order of increasing the value of the array, not its position, we will now make improve the naive algorithm to run in linear time. There are two cases. The first case is when simple algorithm says the answer is 0. These cases are okay even with the most simple algorithm, because when the first characters are different, you find it in constant time. So all zeros are found in total linear time, okay? Or no, you're tired, I know. And we all want to have lunch. It's okay. We have only 8 minutes left until that great moment. So don't worry and try to concentrate for the last time for today, okay? No, for the last time for the morning. Because in the evening you will have to concentrate 10 to 15 times to solve the problems. I will not tell you how many of them are there, but 10 to 15. They are not connected to today's lecture. We have decided that the problems will not be connected to lectures, but probably we will drop in some additional problems to already good contests to cover these topics, but not today. Okay, so the next value in suffix array is some value j. Note, it's not I plus. It's not I plus 1. It's some other value j. So if you have 4 after it, it's 0. So it's some other one. Okay, we found some longest comprimes. It was greater than 0 because 0 case is easy. So let it be non-zero. Okay, these two are equal. Next character is different, and since j goes after I, b is greater than a in this case. So this is great. Okay, let's now look. As I said, we calculate values for LCP in order of numbers. After 0, we go to 1. So here, after I, we will go to I plus 1. Okay? I plus 1 is somewhere else in our array. I draw it after, but it can be before also. It can also be j. It doesn't matter. Okay, it's somewhere there. Where is j plus 1? The answer is it's not necessarily next, but it's somewhere after I plus 1. Why? Take the common prefix and remove the first character. Still, now we have the common prefix of the same characters except the first one, and then a and b, and a is smaller than b. So j plus 1 will go after. Will it go immediately after I plus 1? Or not necessarily. It is possible that it will go somewhere else. But the important thing that it will go after, and since it will go after, all those strings between I plus 1 and j plus 1 start with the same, let's say here we have z minus 1 character. So when we calculate LCP value for I plus 1, we may start with the previous value for I minus 1. And this generalizes to the case that was 0. In this case, we just start not with minus 1, but with 0. So let's say here, for 0 we find 1, so we start with 0 next time. Okay, for 1 is 0, no new, nothing interesting. For 2 is 0, nothing interesting. For 3, it's not defined at all, so nothing interesting. For 4, we find it's 3. So next time we calculate for 5, we know that it will be at least 2. Well, it turned out that it is a 2. Okay, 2 is okay. Next, when we start for 6, it is at least 1. Again, no progress, we have 1. And next time we start for 7, it is at least 0. Well, it is always at least 0, but this time we know it from this picture. And so we have 0 here. So what we need is to know in which order to do this. So we take auxiliary array, say A1, such that A1 of I, A of A1 of I is I. So it's inverse permutation, if you know about it. It's easy to find A1 array for I from 0 to n minus 1. A1 of A of I is I. So we know the position of each character. Now we go for I from 0 to n minus 1, but let's go not for I, for say k. So we take, no, for I, it's okay. For I, we take the position for which we calculate k is A inverse array A1 for I. So we calculate for k starting from the position from the last time. So while, it's similar to that function. So while s with index k plus, so we say that LCP for k is at least z from the previous. So we start k plus LCP. Not k. From A with k plus LCP of k is equal to S A k plus 1 plus LCP of k. While it's okay, we increase, just like in that function. LCP of k plus plus. And then we say that that is maximum of 0 and LCP of k minus 1. And that's it. It has some bug. It doesn't correctly process the last one. Here we have no LCP value for the last one. I think that you can add the required if to this code. Okay, so we build LCP array, and tomorrow, after we discuss problems of today's contest, we will continue talking about suffix array. You can also, if you missed something in definitions or in this algorithm, you can try to recover it tonight, so that you come prepared for tomorrow's lecture. And a small final notice is about team logins for teams. They didn't, any of the organizers who have printed logins, I sent to Raphael and Rudolph. Yes.
I think it's going to be handed out during the contest, or right before the contest.
Before the contest. Okay. We will. Then I will describe you. We will hand you out. Who has no team? Are there any person who has no team? Well, okay. At your option. If you want to try, you can solve personally, or you can create any teams you like for a contest, because it's not a competition, it's just training. However you like. If you feel comfortable solving alone, okay. If you feel comfortable with a new random team or joining some other team, okay, also no problem. So, after you return from lunch, we go to laboratories, I think they're over there, and you will get a sheet of paper with your team number. It's just an integer number, it has no connection to your results. And with a login and password to the contest system, and a detachable part where you write down your university, team name, and your names, and I will push it to the system, so you are okay in standings to show as your team name. And also you will get a printed copies of problems, and you will also have copies of problems online in the contest system, so you can copy and paste examples and so on if you want to test your solutions. So that's it for today's lecture. Thank you very much for listening, and good luck at the contest. And now I think that we can go to lunch. Our organizers will help us and lead us to the lunch. Yeah?